Okay, everybody's back. We can go. So we will talk now a little bit of activation function, but just to give you some information on the different activation function, and we will come back later on what is the most useful in which situation, more in chapter 6. Okay. Ah yes, I put like this better. Yes. Okay, activation function. We have seen we need activation function. Why we need activation function? Because if we don't put a non-linear activation function, we will have something linear. So it will be not gain anything in comparison to the linear model. So the most popular activation function are the sigmoid, which has been chosen at the beginning, but sigmoid is also, keep in mind that it depends on the nature of your data, but binary classification, we use the sigmoid for the output layer. Softmax, you use the softmax for the output layer in a multi-classification task. Linear for the regression, this for the output. And after, for the hidden layer, there are different options, possibilities. So we have the sigmoid, the ReLU, the soft ReLU, the hard threshold, hyperbolic tangent. This is the most popular, but there are more. Okay, so what is important on the nonlinear function is to understand the derivative too, because the derivative is very important during the optimization process. And it gives you maybe some insight why to show which kind of activation function. So as I told you just before, the sigmoid was mostly used historically, and if you're looking at the shape of the sigmoid, so the sigmoid is going to from infinity to R to 0, 1. So the output is 0, 1. And you can see that it's saturated at 0 and 1. So you have a plateau at 1 and a plateau at 0 for high value of Z, and very low value of Z. So this keep in mind if you're looking at the derivative. So the derivative of the sigmoid is, we will use this during the backpropagation. In fact, if I try to derivate the sigmoid, is in fact the sigmoid multiplied by 1 minus the sigmoid. And this is the shape of the derivative, which is maximum at 0.25. And you can see that, of course, when on this stage here is like a plateau, and this is a plateau. So on this part, it will be close to 0. Okay? So is the meaning that the sigmoid, I say, saturate at the tail with value of 0 or 1. Okay, so it will make sometime a problem to call the vanishing gradient. So it's the meaning that your gradient will be smaller and smaller, and after will be close to 0. And so if your gradient is close to 0, it's the meaning that it doesn't move any stage, and your gradient doesn't move. So this, keep in mind this point. And so now is the reason of this that the most popular now is becoming the most popular is the ReLU, rectified linear units. I'm very bad to pronounce this ReLU. I don't know how to pronounce ReLU. If somebody can pronounce for me ReLU, because it's really, I speak really like a French when I say ReLU.
I just usually say ReLU.
ReLU, so ReLU. Okay. Thanks, Andrew. So ReLU, I will try to do it now. ReLU, so it's a rectified linear unit. So how it looks like is 0 for negative value, So no activation. So if your linear combination arrive in a neuron, it gives you a negative value, your neuron doesn't activate. And if it's positive, is activate with the linear, the identity. So this is the shape of the value, which is a non-linear. Even it looks like linear, is non-linear function. So if you're looking at as a derivative, the derivative is like this. So it's 0 for value which is negative, and it will be 1 for positive value. So it makes that the drawback of can be we call it the dead ReLU. So is meaning that your neuron die to 0 for negative value, and so this can cause some problem for backpropagation, because for negative value you have a derivative which will be equal to 0. So an alternative is called the Liquet ReLU, which is a variant of the ReLU. So instead to have 0, in fact, it is defining as the max of alpha z and z. So with alpha, a tiny value. So you can see that the Liquet ReLU, the shape of the Liquet ReLU, if I zoom, is not 0 now for negative value. Something close to 0, but it's not 0. So it's a meaning that your derivative for negative value is not equal to 0, but it will be equal to alpha. So this has been the reason of, okay, I think Andrew have a trouble because I can see his face. He's just like, something wrong. I don't know what is wrong, Andrew. Okay, and so I will go through some activation function, but I will go fast, and you can see after some activation function. So which is also one is quite famous is the tan hyperbolic, which squash is like you can see that is like it looks like the sigmoid, but the sigmoid is going to as the output to 0 and 1, but the tangent h, which is tangent hyperbolic, is going to -1 to 1 with this shape. But there's the same trouble as the sigmoid, because you will have also for very low values a derivative to 0, and so to very high value of x, you will have also a derivative to 0 too, because it's a plateau. So the tangent is just like a horizontal line. So it's a meaning that the derivative is equal to 0. So the value of the derivative is, you can check if I'm doing a mistake, is 1 minus the function square. Okay. So I give you a task, but we will not get too much time to do the task on live. So my advice to really understand what is going on is to do once by hand. So I just put here the same thing on the chapter. You have 3 features. You have one hidden, so it's a two layers neural network. We have just one hidden layer network, and I have just used as activation function at the end to simplify identity for the activation of the output. This is my neural network, and I want that you are comfortable to derive the backpropagation algorithm for this neural network. So I remind you what is the backpropagation. First task is to do the forward equation. So I put here, just have a look at the forward equation. And I have used the ReLU for the activation function for my first layer. So first layer is ReLU, and the output layer's activation is identity. So is the meaning my task is a regression task. So for this one, my first question is which cost function to use? I don't remember. Please. You have to reply. Which cost function? Sum of square. So the square loss. Okay, you are sorry. Oh, it's good. I'm sorry. It's okay. No worries. You can try. So it's a square loss. This is a regression task. So the square loss. So if I write this for the full, it will be 1 divided by m sum of y to m to y hat. I will put a I here minus y high square. Make sense? Okay, and after you have to deal with the dimension of each object. So it be easy for you now to understand, but try to do by yourself the question 2. So we'll not do now. Yes, no, we don't do now because we are a little bit far away. Okay, so this is your homework. And after, for doing the back propagation, you need to compute the derivative using the chain rule. Make sense? So you need to compute all of this. Just check something. If I put this, and I think I put the solution on the... So first you need to divide the cost function to W and so on and so on. So you need to try to think about all of this step. Okay? So this is a side to do homework. And I put the solution of the slide is there. But try to go to this step. But I think you did this during your assignment because you had to program this during your assignment. Make sense? So try to do this, and tomorrow if you have some question, if I put some typo on this, you can tell me. So I will not go to all of this in the question, and I recommend you, suggest to each time when you do the derivation or all of this step, try to indicate the dimension of each object. It will help you. Okay, so you have the algorithm. And this is finally the algorithm of the backpropagation for a 2-layer neural network. Okay. Take-home message. So it was the first lecture. So try tomorrow to write what for you is the perceptron, the multi-layer perceptron. What is for you the meaning of activation function? Try to tell you, I know this activation function, how is the derivative, and so on. Think about the backpropagation and what is the meaning of dead neuron. Okay, now we're going further. So an extension of this we have seen is the general case with R layers. And on the chapter and on the slides, you have the derivation of the backpropagation algorithm for general fully connected multi-layer networks, which are defined by this equation. So at each step, I use for each layer, the first layer hidden 1, the hidden 2, the hidden layer R-1 is I use a ReLU activation function. And it's just an extension of the first example. And for the last layer, I use what I use. the identity function, you can see. So a regression task. And as a cost function, I use, this is for one sample. I use the square loss. So is it a bit tricky also to derive the backpropagation? It's a little bit hard at the beginning, but it's very important to do this exercise or to follow the step. It's very help you to really understand what is going on the backpropagation. So if you manage to go through this equation, after it's forever, you have understood the backpropagation and how to derive the backpropagation using the chain rule. And you have the algorithm there. Okay. And now we talk something which is are not on the it will be useful to again understand the backpropagation, but it is not on the chapter notes. I will talk about now about how to do derivative. So we have seen that we will use the backpropagation, but in fact the backpropagation is a part of the automatic differentiation process. I will explain now because you can see this word in many places in deep learning. So how to do some derivative, you know that when you did some math, you can do some derivative analytically sometimes. But in fact, we don't need to do this because we need something tools to get something fast to get the numerical derivative for optimization. You can use also some software to get some symbolic computation like Mathematica, Maple, or another software, apparently Tinao for deep learning. And so this, I put just an example, but I don't have ln. Where is my ln? Where is my function? Oh, yes, it was an example from this paper. I need to go to this paper. I don't remember which function I use here. Ah, yes. So this is for the function which is in this paper. We propose to compute just to show like an highlight that equals the logistic map, which is defined by ln plus 1, which is equal to 4 ln 1 minus ln, and with L1 equal to x. So this is my function, and I want to do the derivation of this function for each value of n. So L1 is x, the derivative is 1. L2 is 4x 1 minus x, you can see here. And the derivative is this, and this after is L3, and you can see the derivative, and so on, and so on, and so on. So the main issue that says the expression is squared. So it's not so good to have even some symbolic derivative because of your derivative. So you can do, we have seen with Sarat yesterday, some numerical differentiation. So the numerical differentiation, you know how to, this is definition, if you have a function from Rn to R, you can compute the gradient using this formula. You need to numerically to specify a small h to get an approximation error, the smallest as possible, but you need some, so you still have an approximation there. You can control this approximation, but your derivative will still have an error, and you can do better by the wider order for difference, so you can compute the derivative like this. So this is numerical solution. But in fact, in deep learning, we don't use also this because it increases the complexity and you still have an error. So if you want to go back to more in detail to automatic spelling, differentiation in machine learning, you have a nice survey, and you have, if you, I think, I don't know, I didn't put the link, but I can put the link of this nice paper, which is called this paper. I have this paper in mind, which is called, yes, Automatic Differentiation in Machine Learning, a Survey. And we put on the website this reference, which is quite a nice paper. So what is the automatic differentiation? So I take the definition from this colleague, Roger Ross. We say, refer to a general way of taking a program which compute a value and automatically constructing a procedure for computing derivative of that value. So the idea is to decompose your target function to an elementary operation of symbol function. So this is a key point. And by the second key point, we will exploit the chain rules to a computational graph. So you know all this word, you know chain rule, you know computational graph, and you know elementary operation of a function. So it will be quite straightforward to do the automatic differentiation. So the automatic differentiation sometimes is assimilated to backpropagation, but in fact, the automatic differentiation, there are two ways of the automatic differentiation. There are the forward mode accumulation and the reverse mode accumulation. And the automatic differentiation is useful to compute some derivative. So it's based on an augmented algorithm by proposing a graph on simple elementary function. And I think the easy way to think about this is to do an example. So this our example. We want to compute this, we have this function, our target function. And for example, we want to get the derivative of this function in respect to x1. So in fact, I want to compute this by using the automatic differentiation, and we will first compute by the forward mode. So first, in this paper, they propose to build the computational graph, which is based on elementary operation. So you see the graph, this graph, and you will tell me on this graph what's the meaning of this each V1 and so on and so on. So in this definition of the automatic algorithm, Vi minus n is equal to xi as the input variable. So in this example, we have two input variables, x1 and x2. So we have v0 and v1, v minus 1 are x1 and x2. Makes sense or not? So we need to make sense. Now we need to develop the computational graph on elementary operation. What is the elementary operation? You can see that there I have logarithm of x1. So v1, what will be v1 for you? Yes. So I will put is, with our notation, is ln of v minus 1. Okay? v2, what is for us v2? Yes. So v2 here for us is v0 multiplied by v minus 1. So the elementary operation is multiply. Yep. And after, what is V4? Oh no. You got it, you got it, you got it, you got it. Tell me V4. Yes, the plus. Okay, everybody got it. So we go faster. V1 plus V2. Okay. And V3, so V3 is taking the sinus of V0. And V5 is only just V4 minus V3. Is okay? Okay. So you decompose by this, and now the forward mode, you select a variable of differentiation. So in our case, we select x1. So we choose here, x1. So it's the meaning that we will try to compute f just one variable. So we try to compute this. Okay? And now we augment each working variable with this notation. So it's a derivative of Vj derivative in respect to x1 here. And run a forward pass. And x1 is equal to 1. What is the meaning that x1 is equal to 1? x1 is the definition of the derivative of in comparison to x1. Yeah. So we go through this. Okay. So here you have the forward. So you start by x1 is equal to, okay, I say it, and run a forward pass. So I run a forward pass. Okay, forward pass. I start by an example that x1 is equal to 2 and x2 is equal to 5. So after I go through all of these steps, forward pass, and you compute that y is equal to this value. Makes sense? And now you do the forward tangent, so the derivative. So we say that this is equal to 1. Are you agree that v0 dot is equal to 0? Agree or not? Yes. Okay, everybody is agree. And after y v1 dot, oh, yes, v1 dot is equal to v minus 1 dot divided by v minus 1. You remember what is equal to v1? Yes, v1 is equal to ln of v minus 1. So the derivative is make sense? Or not? And the definition of v1, remember, is the derivative of v1 divided by x1. So you want to have the derivative of v1 by x1. So if you use the chain rules, it will be the derivative of v1 in comparison to v minus 1 multiplied by the derivative of v minus 1 divided by x1. Agree? Yep. Yep. Okay, and 1 over 2 because it's 1 divided by x1, and x1 is equal to 2 by over 2. So you go through this step for all this computation. So you compute at each stage in the forward pass the derivative, and using the chain rules, you end up by the derivative of your function in respect to x1 to the point 2, 5, you got 5.5. So I'll let you at home to go to all this to understand the process. It will make sense normally. And so this is the forward mode. So the forward mode for the automatic differentiation is quite nice and efficient for function with going from R to Rn. Okay, so your function, and you need to compute, you have seen that we compute the derivative just in one forward pass. You just need one forward pass, you get the derivative. It's quite nice. But the trouble, if you have a function which go from Rn to R, you have seen that we have done one forward pass, but we managed to compute just the derivative of f in comparison to x. But if you want to compute also the derivative of f in respect to y, you need to do again this process and to do again this process to every variable. So to get the full gradient. So it's not really efficient if n is getting greater and larger and larger. And in deep learning, remember that we have a large training set. So we have not training set, we have a lot of features. So if we have a lot of features, so it's D is really big, so we need to do a lot of time this forward pass. Agree, agree, agree. So this is the way that when you have a function like this and we want to get some derivative, to do some optimization, and when n is larger, greater than the dimension of your output, which is most of the case our case, because our output generally is in irrigation is just one value. If it's in softmax multiplication class problem is k values. So most of the time, in fact, we not use the forward automatic differentiation. So we use the reverse mode. And the reverse mode, in fact, is just the same way as the back propagation. So the back propagation can see as a special case of the reverse mode of the automatic differentiation. And the two origin papers are in 1979 and 1974. And in fact, it has been brought to fame in a nice paper in Nature in 1986. So we go through the back propagation, the reverse mode. So is the automatic differentiation. So first stage, you run a forward pass. You select, second step, you select a dependent variable. So for us, the outcome. And at each, you augment each intermediate value, which is, oh, sorry for this. I'm not the best with the tablet. Huh? Come on. Sorry. Don't be sick. Yes. Yep. Yes. And at each value, you compute at this notation, which is, I used this notation last time, vi bar, which is a derivative of your dependent variable in respect to vi. And you compute using this, using the different path and the child of your node. So if we do this in action, it will be easier. Maybe we see if we're going on. So this is a table from the paper. So you can go through the paper if you want more details, but I think you will be able to understand this part. So same process as we have done before, but we do in the reverse mode. So remember, even in the back operation, we do a forward pass. The forward pass enables us to compute the value of our outcome. So in this case is y, which is equal to f x1, x2. And now we do the reverse. So the reverse, we start by this part. So this first stage is always the same, is the derivative of y v phi bar is the derivative of y bar, which is the derivative of y to y, so is equal to 1. Come on, it's equal to 1. And after you go from this path and you want there, so is you want the derivative of f. Oh, but why is like this each time? Derivative of f, so is derivative of v5 compare in regard to, oh my god, I'm a mess. Okay, what is the definition of v4 bar? If somebody can tell me what is the definition of this? Is my notation derivative of y in comparison to v4. Agree? So derivative of y to v4 is, what is this? Y is v5, so is derivative of v5 compared derivative by okay, this is a mistake. I let you do it. My question is, y is equal to this. Okay, so this is 1 multiplied by the derivative of v5 divided by v4. Agree? Agree or not agree? Agree. Okay, not agree, I don't know. Okay, I'm going to speed up. I will to speed up because I want to go to solution. So if you're going this and this way, try to do it, and I come back tomorrow very quickly if you have some trouble to this step. It's just you need to go through the path, and the key point is at this. To compute this one is coming back by this way and this way, and also to compute this one is going back by this way and this way. So you will get a sum, and you can see the sum because you are there. Is this step is there and there. Okay, and so also for v bar minus 1, you have this minus 1 and there. Okay, I'm starting to do it messy. So relax, do by yourself, relax. Are you lost or not lost? A bit, yes. A bit lost. Okay, so I don't like to be lost. I'm just looking at what I wanted to go. Want to play. Yeah, okay. I will not have time to go directly to there, so it's better to finish this 5 minutes by this way. Okay. If you're too lost, we can come back. We can do it again. We do. If you want, I can do it. Ah, I am happy with this. What? To do it or not to it? Yep. Okay. You want more explanation in the last 5 minutes, or I keep going? If I have two yes, I skip the 5 minutes left to do this, or I'm going. Keep going. Yes, please explanation.
Benoit, you know, the V bar minus 1 and the V bar 0, they're separated into two parts. Is that because of the two arrows in the algorithm that you don't do them in one go?
Repeat again.
So just in that reverse adjoint, the
Yes.
top sort of 4 V bar minus 1, V bar
Yes.
0, V bar minus 1, V bar 0.
Yes. In fact,
they're all separated.
Okay,
Is that
okay.
just because of the algorithm?
Yeah. Okay. I will explain. It's better I explain here. I will try to explain this, and so it'll be clear for everybody. Sorry, Christina, I keep going on this one, and it will be very clear to everyone after, I hope. Okay. So now I want to compute the derivative. In fact, I will get the good thing with the back, the reverse mode, we will get the derivative in respect to x1 and also in respect to x2. What we don't have in the forward mode of the automatic differentiation. Okay. So I start by the first thing. I will do all the equation. Okay. So this one, you get the v5 or not? v5 is the derivative of y in comparison to, is it? Okay. To v5. And this, okay, that is equal to 1. Make sense? Yep. Okay. Oh no, please don't do this, Benoit. Come on. Okay, now I'm going to v4. Oh, come on. Each time I touch my tablet. Okay, come on. Relax. Okay. V4 bar channel. Make sense or not? Or not really? What was the V5 in comparison to V4. You here is here, V5, V4. If I derivate V5 to V4 is equal to 1. You can see here. Make sense? Yes, yes, tell me, yep. Okay, now I'm going, I got V4, okay, here. Now I want to have the, which one is tricky. So the good thing is after you forgot all of this, so you got there, and if I want to get, I don't know, I will say V1. What is V1 bar? V1 bar is the derivative of, you just need to come back to the V4, in fact, V4. What is it? V1 is V4. So the good point is when you compute a graph, you forgot all what you have done before, and you have on the just V1 is just connected of this one. This is the parents of V1. So you have a V4 bar multiply by the derivative of V4 in respect to V1. And V4 to V1 is again 1. Okay? So V1 bar is V4 bar multiplied by 1. And now I'm going to math, okay? So which one you wanted is the tricky one. It was V1, this one?
Yeah, no, it's more, I was just wondering why they were separated instead of why they were done at the same time, but that's bad.
Yes, so this one is, if I want this one, the V1, V minus 1, which in fact is the derivative of x1, x1 bar. You can see that x1 bar is V minus 1 bar, which is the derivative of f, which I wanted. Eh? So how to get this? You look at the parents, so it's V1 and V2. Yep.
Yep.
So in the paper, instead, so you will have a sum of 2. You compute first, it doesn't make any difference. So you compute first this part, so is respect to V2, and after you compute the respect to V1. You see, or not really? Or a mess. You can see this one is related to V1, and this one is related to V1, but you do V1 equal V1 plus. You can do in one shot, is a 2 pass. Make sense?
Yeah.
So you have this one derivative in respect to V minus 1, and this one in respect to V minus 1. Yep. And you add.
Yeah.
So you add these two. I hope I clear it a bit in 5 minutes. Yes, so Alex is a good point. Now, these two methods, we have seen what we have seen. In the forward mode, if you do one in the forward mode, at the end, you got the derivative in respect to one features. But do you, with the back propagation mode, in fact, you have in one shot on the back propagation, you have the derivative of x1 and x2. Yep. So why is the reason why in the automatic differentiation, we use the reverse mode for deep learning and is the back propagation. So there are some package in TensorFlow which is used manipulate gradient. It's called AutoDiff. You can go on this, and there are different library in PyTorch, TensorFlow, and so on. If you want to use, even not for doing the computation, but if you want to just derivative a function and so on. So it's not only used for deep learning. Deep learning exploit the automatic differentiation in the reverse mode. That's the conclusion of this part. Any question of this? Oh, and I say, okay, because I want some people I can see that they like playing. Say, want to play? You can play and try this. I put solution here, but I didn't put the solution. Any question? Because I don't want to go further because it will be too long further, but we have some important things to see tomorrow and quite nice. So I know that is a lot of work from you. Try to go through what we have seen. Just read again and read the slide, not try to understand all, but read the slide just to be not just surprised what we have seen. And I will go through some important points and not, I will emphasize and highlight some specific point, but I will might be not be able to go through all of this slowly. Okay? Any question?
I just wanted to ask two things. Firstly, Unit 5 still says this unit is under construction. When will those notes be ready for student consumption?
For Unit 5?
Yeah.
I will, Unit 5 is Yoni who teach this, so I hope soon, because it's next week, Unit 5, is it?
Yeah.
Yes, I will ask Yoni and tell you tomorrow, okay?
Awesome. And the other question was, for the quiz, it says we're going to be tested on Unit 2 and part of Unit 3. For Unit 2, would we be better off using the slides that you used, or the notes online, or both, or it's not going to matter?
Unit 5 doesn't matter because you need to do a summary. You use a summary.
Yeah.
Yeah. So for the unit for the chapter 2, yes, both document.
Awesome. Thank you.
I think it's similar, the chapter 2 and the slide I've done. So it be I made the question 2 is not so too hard. So you have the information of the chapter on the slides or on the. We have seen this during the lectures, in fact. Is the hint. The question on the chapter 2 have been seen during our lectures. Okay, no comment, nothing. Can I see a face? A friendly face? We have still 30 people, it's good. No face. Okay, so I see you tomorrow. Thanks, Cathy, to give me, thank you. Thanks, everyone. I hope it was, you learned a little bit some stuff today. It was a goal to learn every time 1 or 2 things per day. And I can see that some people start to speak French, so it's good. I will try to speak English tomorrow, I'm sure. Have a good evening. Work hard, work in progress. Enjoy working. Thanks, Matthew. The value. I think I listened some people, I don't know, maybe it was French, they say relu. But I was thinking it's weird. So I will check again. Have a good evening and keep going. You're strong. You did good, well. You did well as the assignments. Good.
Thanks, Benoit.
See you, Augustin. Okay, so have a good evening. Three participants derrière. Ah. One guest is still on live. You're sleeping. Xu. You still there? Xu. Okay, Xu, I'm leaving. Hello?